Hey there, my name is Gokul, and today I'm going to be talking a bit about imitating an expert who has access to more information than the learner. This is joint work with Drew Bagnall, Stephen Wu, and Sanjay Chowdhury. Let's consider the following toy problem. We're playing a multi-armed bandit where only one arm per round gives a player money. This context is revealed to the expert, but not to the learner. So, if this problem is a single time step, the learner can't hope to do better than randomly picking an arm. But if we instead allow the learner to interact repeatedly with a set of arms, let them receive feedback of some accuracy of whether they picked the correct arm, one might hope that, given enough time, the learner can narrow down which arm is the correct one. Okay, seems simple enough, right? Let's try and solve this problem via imitation learning. We're going to generate trajectories from an expert who pulls the correct arm with some probability. Then we're going to try and imitate them by letting the learner condition their action choices on the entire history of past states and actions, so they can try and narrow down what the correct arm is. We're going to compare two kinds of imitation learning algorithms: on-policy algorithms, like Gale or Dagger, and off-policy algorithms, like behavior cloning. First, let's look at how an on-policy learner does. Here, a green dot corresponds to matching expert performance after a few thousand time steps of information. Epsilon observation is how often the feedback is flipped, and epsilon expert is how often the expert makes a mistake. So with epsilon observation equal to 1/2, your arm correctness observations are flipped to 1/2, so no algorithm can learn correctly. But outside of that, we see the on-policy algorithm work everywhere. In contrast, the off-policy learner has these sort of phase transitions in terms of whether it's able to perform as well as the expert did, meaning that a small perturbation of problem parameters can lead to drastically different effects as far as consistency. Let's dig into what happens over time steps of the problem at one of the red dots. It turns out that the off-policy learner ends up picking the correct arm with probability no better than just random chance. On each rollout, the off-policy learner picks a random arm at the first time step and just keeps repeating it for the rest of the episode, completely ignoring the thousands of pieces of feedback it has received that's picked the wrong arm. Let's synthesize the preceding observations. First, the on-policy results show us that outside the middle row, it is possible to match X performance given enough time steps of information. Put differently, we're in a sort of asymptotically realizable problem, where the learner is able to match expert behavior given enough time steps of feedback. However, off-policy approaches appear to not take advantage of this asymptotic realizability, and instead can choose policies that perform quite poorly, and just end up repeating past actions. While the preceding example is quite stylized, we see an analogous problem in practice, including for self-driving. We call this the latching effect, where an off-policy learner that's equipped with history ends up just repeating its own past actions. I'm now going to try and explain why this happens. Let's try out a few graphical models. First, we have the expert trajectory generative model, which has all actions generated by an expert who sees the hidden context C. Next, we have the on-policy graphical model, in which all actions are taken by the learner, who only has access to the context as it shows up in history. Lastly, we have the off-policy model, which acts as though the expert was acting up to the point that the learner takes control. Now, in actuality, the center model is what's happening. The learner never sees the context. However, because off-policy algorithms assume the chimera on the right, they end up treating their own past actions as if they were the experts, as though they had information about the context, even though they didn't, which is what leads to the latching effect. We can see this point mathematically by writing out the posteriors over context you would generate under each of those graphical models. Notice that the on-policy and off-policy posteriors differ only by one term, the probability of the expert taking an action. The second equation tells us that off-policy algorithms literally weight their own past choices as though they came from an expert who actually knew the context. This is why the learner keeps playing the same arm it first played, because it assumes the expert was the one who picked it. While the preceding argument focused on Bayesian learners, we prove a general theorem of paper that applies to all on-policy and off-policy learners. Roughly, it says that on asymptotically realizable problems, an off-policy learner is bound to pay for the rest of the horizon for unavoidable mistakes made early on. In contrast, as long as an on-policy learner is able to eventually drive down their error, they will be able to match expert performance. We also see this latching effect on examples from the PyBullet suite, where equipping an off-policy learner with access to history can drastically reduce its performance, while we do not see the same effect for on-policy algorithms. With that, I'd like to thank you for your time, and please check out our full paper, code, and videos at the link on the screen.